So now that we've developed this set of numbers that is separate from or different from our real numbers, we want to introduce the idea of creating numbers by combining values that come from the real number system and values that come from the imaginary number system. So we create something called the complex numbers. This is a system of values that can have both a real part and an imaginary part. So a very strange aspect to this is that when you see this form, this a plus bi, we're saying there can be a number here that if you looked at that number would be a real number, and then there could be a number with an I attached to it that would be considered an imaginary number. And together, combined, but again, they're not like terms, that is what's referred to as a complex number. So it's strange to think of a number as actually multiple terms together, right? Usually you think of a number as a value, but now we're saying this form, standard form of complex numbers, that would be considered a complex number. So with that in mind, the idea is, again, it can have either part. So complex numbers could be just a real number, just an imaginary number, or the combination of the two. So complex numbers are this much bigger system of numbers that include every real number, every imaginary number, and all the combinations of them. So with that in mind, we're not going to do a whole lot in this chapter or in this class with imaginary numbers, but we will deal with things involving I and powers of I. So we do want to revisit the thing we saw briefly on the previous page, and now we'll kind of officially define it. That when dealing with I, the imaginary number unit of square root of -1, if we ever encounter I squared, as we saw on the previous page, we're going to say that I squared itself is just the number -1. Because again, if I is the square root of -1, then I squared is the square root of -1 squared. And that's that idea that you square a square root and you get what's inside. Okay? Now, with that said, we can look at other powers of I. And although this does not happen often, it's just kind of an interesting pattern to point out that does exist. So it says, let's see what else we can determine about the properties of I. So if we know that I is going to always be represented as I, that's just its default form. But we just saw that I squared, you can think of as I times I, and actually get that value of -1 out of it. Well, what about I cubed? So I cubed, that's 3 i's together. Well, that'd be the same as thinking of it like 2 i's and one more I, right? I squared times I, that's a total of 3 i's. And we just saw that I squared is a -1. So that's -1 times an I. Or in other words, we don't really need the 1 there. So that's like a negative of I. So I cubed could be thought of as -I. And then the next power of I to the 4th. If I thought about that as, oops, that's not supposed to be there, I squared times I squared, right? I to the 4th would be like 2 i's and 2 more i's. But each of those I squareds is a -1, and -1 times 1 is a +1. So if we ever encountered I to the 4th, that would just be the value of 1 itself. Again, nothing involving I. Now, with I to the 4th being back to a 1, what happens if I look at I to the 5th? I to the 5th, well, I can realize that the first 4 of those 5 i's, I to the 4th, if I can separate them out, they're just going to be the number 1. And if you multiply something by 1, it doesn't even need to be there. So that 4 i's there, that power of 4, doesn't even really affect anything. And notice we're back to the value of just I. 1 times that remaining 5th I, but it's only 1 I by itself. Well, that same trick can be used as far into the cycle as you want to go. I to the 6th, actually that's the question right here on the bottom of the page, I to the 6th. I can think of as I to the 4th and I squared. But the I to the 4th is just a 1. And in this case, I squared is a -1. And so that would result in the value of just -1. But notice that's the same as just going to the I squared row of this 4-row pattern. I, -1, -I, 1. And then it would start over with I to the 5th is I to the 6th is 1. That would mean I to the 7th is -I, and I to the 8th would be 1. because again, I to the 8th would be 2 groups of 4, right? It wouldn't matter how many groups of 4 there are, because it's just a 1 times a 1, that's still a 1. So this pattern just keeps repeating itself every 4 i's, essentially. So what that means is, for these different questions, you don't need to walk through this entire path every time. You just say, I to the 13th. Well, the first I to the 12th would be 4 and 4 and 4. Right? There's 3 groups of 4 in there. Every one of those is nothing but a 1. So 1 times 1 times 1 times I is just I. We can always simplify these powers of I down to one of these 4 things, either I, -1, -I, or +1. So I to the 27th, right? Again, just look for the biggest power of 4 that you could pull out of there. You could pull out 24 i's. And again, it doesn't matter that that's 6 groups of 4. It doesn't matter how many there are. Every one of those groups turns to a 1. All you care about is what's left, the I cubed. That all turns to a 1, and I cubed, if you have to write it out like we did up here, that's fine. I cubed is I squared and I, so that goes to a 1. Now this goes to a -1, so you have -1 times I, or -I. Like we saw, I to the cubed will always be a -I. And then I to the 32nd, 32 is divisible by 4. That means there's an even number of groups here of 4. There's 8 of them. We don't need to write them. We don't need to know there's 8 of them because every group of 4 turns to a 1, which means that will simplify down to just a 1. So the only real operation we're going to be doing with imaginary numbers here in this section is just these basic add, subtract, and multiply. Certainly more can be done with them, but in terms of what we're doing at 7-7, this is all you have to know. And it's effectively going to be similar to working with polynomials, really. Just watching out for the I squared quantity. So, like here, adding these two, that plus sign telling me these parentheses aren't even important. So really, you've just got all of these terms out in the open, and you're combining like terms. 3 and -5, and -2 and +4, giving me that. And that's it. That's as much as you can do, right? That's actually a standard form, a plus bi, for the complex number. Now for subtraction, we know we have to distribute. We can drop the first set of parentheses, but we have to make sure we understand that second set was important, helping us to do that. Now we can combine like terms, 3 and 5 giving me 8, -2i and -4i giving me -6i, and that being the final result there. All right, the next one here, multiplication. Just like polynomials, we're going to distribute first term to all the terms, so -15 plus 12i. Second term will distribute plus 10i. Now here, this last arc, -2 and 4 is -8, and I times I will give us an I squared. From there, we want to make sure we remember that I squared is like a -1. So this is really the term plus 8, right? -8 I squared is like a -8 and a -1, so it's a +8. So those are like terms there that we can combine and get -7, and then our I terms combine to 22i. So that's the one thing we have to watch out for with these complex numbers, is that I squared quantity and how that affects the combining of like terms. And then here, as I mentioned in an earlier video, very important to make sure you always remember squaring a binomial means to write it out. The binomial times itself, then you can think about your arcs. So 9 minus 6i, and another -6i, and then here, this last arc, -2 and -2 is a 4, I and I is I squared. Again, that is a -1, so that last term is really a -4. 9 and -4 is 5, and -6 and -6i will be a -12i for our final answer.